All right, today's group meeting, we have Eriksson and Tjoa is going to talk about quantum imprints of gravitational shockwaves. Eriksson, whenever you want.
Okay, thank you, Eduardo, for the introduction. So today the talk will be a little bit rough on the edges, so you will have to pardon me for a little bit. Also, every Wednesday I've been not being able to sleep for some reason, so please ask questions if I'm not being clear myself. So this is a collaboration with Finn Gray, David Kubisnak, Talsha May, and Sydney Timmerman. The last two are current PSI students, so this was a project that we proposed as part of the winter school this year. So we will be talking about quantum imprints of gravitational shockwave. So it is something of similar flavor to what David gave the talk in RQI, but there will be some differences. Give me a second. So the outline is basically these three. So I will first take you a detour towards gravitational memory and asymptotic symmetries, and then I will bring it down back to what is a little bit more familiar to us, which is the GR and the QFT of some curve, some non-trivial, non-flat background, and then after that we'll go back to Unruh-Dewey detector, which more or less everyone in this group will be familiar already. Okay, first, gravitational memory and asymptotic symmetries. Okay, so first, to say that gravitational wave have memory effect, it really means that the late time minus the early time has a non-zero difference in the strain, whether it is in the either polarization. So what happens is that there is a kind of like a DC permanent displacement DC effect kind of thing. So for example, the classical way of thinking about gravitational wave on a ring of test particles is that if a gravitational wave passes by, usually after the gravitational wave has gone, the ring should return to its original position. But gravitational memory means that actually, after the whole wave has passed, this thing doesn't actually return to its original configurations. So Tissot diagram is just a classic terminology that some people have used. You can Google it. It's an interesting concept from 1800. But the moral of the story is that it has been shown that gravitational waves do generally generate gravitational memory. And this memory has both the linear and non-linear components. So for example, the linear one usually comes from non-oscillatory motion of the source. So for example, maybe two particles out there in the outer space colliding, scattering under hyperbolic orbits, or even gamma ray bursts ejecting neutrinos from supernovas. All these things will have linear memory that you can look for. And then there is also a non-linear memory effect. It really comes from the fact that gravity is inherently non-linear equations, right? Because this is basically the same thing as saying that the gravitational waves also generate gravitational waves. So you might recall this from, for example, photon-photon scattering in the higher energy processes in QED. So when you look at the plot, for example, right, maybe the best one is to look at the right one, because the left one maybe is not so familiar to most people. But the right one is a gravitational wave templates during a binary black hole merger. So if you actually can catch the gravitational memory, then what happens is that this blue curve, can you see the cursor?
No, I can't see any cursors, no.
Okay, here.
Oh, now I do, yes.
Okay, so apparently double screen means I have to go to the right screen. Okay, so this blue one is when you have a permanent displacement due to gravitational memory, while the red one is the one that has no gravitational memory. Now, the question then now arises, right? If I say that this is generic, then why are LIGO selling the red one, right? And the answer is really because in general, for terrestrial experiments, gravitational memory is a bad thing to try to detect. What happens is that for you to be able to store memory, right? What happens is that you really need, for example, a ring of test masses to actually kind of let it freely go into its new configuration. But for stuff like LIGO, right? What happens is that they are literally hanging like 40 kilograms mirror on a string, on a silica fiber string. So what happens is that once the gravitational wave pass by, right, just by the local gravitational field, it's gonna rearrange itself to its new stable configuration. So the technical way of saying this is that terrestrial experiments, most of them do not store memory. So this is really what happens. So that's why people are looking at, the first thing people mention is that stuff like Lisa would be the first thing they will look for, simply because the arrangement is not constrained by this setup. And this memory has been looked for like 40 years already. And another important thing is that this is not even a subleading effect. So the memory effect comes at the same post-Newtonian order as the standard strain in the gravitational wave calculations that you see in LIGO.
So quick question, Eriksson.
Yes.
Why don't we see this effect in electromagnetism if there is a linear memory effect and it's very similar, the propagation of
yes. So apparently, right after people bring up this nonlinear memory, right, the first thing people do is that, look, electromagnetic memory should have something like this, right?
Yeah.
And I think there might have been some attempts to essentially do this, and I think if you Google the paper, there will be electromagnetic memory. But I think what people want to look for is gravitational memory for some reasons that I'm not familiar with. So this is one part where I cannot really tell you why people are not looking for this. I think people must have done this to some extent because I have seen papers on electromagnetic memory. So you are absolutely right. And then the next thing is that this is kind of like, so this talk is gonna sound like I'm jumping around a lot. So the next question I would be asking is that what is a 3+1D asymptotically flat spacetime, right? So the answer is actually quite complicated because, for example, you cannot really quite argue by looking at Schwarzschild metric and say that asymptotically flat means that the 1/r kills off the 2m, right? What happens is that you really need the fall off to be correct, not just at I0, but things has to fall off correctly at scry plus and scry minus. And essentially one way to do this, which comes since the 1960s when people first look for serious studies of gravitational waves, is that when you recast this in, for example, Bondi-Sachs gauge or coordinates, right? This is the rough leading fall off that you should expect for asymptotically flat spacetimes. Now, unfortunately, this is not the only possible one. So if you Google online and you have heard this thing called the Newman anti-metric, which is another variation of this fall off, you will realize that the leading blue one is the same. A lot of the red ones are the same, but the sub-leading in the triple dots one are different. And now you might ask, which one should we choose? The answer is, unfortunately, we cannot choose this by theory. We have to choose this by experiment, because it has to do with the higher rate fall off that is not kind of like far away from the source. And hidden in all these things is that you have to really know, like the one of the important parts of this story is that you need to keep track of the asymptotic data. So for example, when you compute the mass of an isolated system in this spacetime, right, you will be tracking, for example, the MB, which is what they call the Bondi mass aspect, and NA, which is the angular momentum aspect. So this would be what, for example, in Schwarzschild black hole, you integrate over some sphere and you get you get the ADM mass and ADM momentum. And respectively, you can also get Bondi mass and Bondi angular momentum. Now, the CAB is the gravitational wave equivalent of the A mu in electromagnetism, with a lot of subtle differences because it's not abelian gauge theory and stuff. And then the NAB is analogous to the F mu nu in the electromagnetism. So it corresponds to like the field strength of the radiation piece of the gravity. Now you might be wondering why I'm using AB instead of mu nu. The reason is because these tensors are really as part of asymptotic data. So they are really belonging to three-dimensional hypersurface of the scry plus or scry minus. So they are not really part of the whole bulk. So I've mentioned this briefly just now. So roughly speaking, the important bit really here is that in this way of writing, it might be a little bit obscure to you, but essentially these things are data you need to keep track of at scry plus. Now there's writing the angular piece in terms of z and z bar. This is basically the complex version of stereographic projection. You might have seen people do stereographic coordinates for spheres. So apparently by using these stereographic projections, for example, the only thing that matters for the CAB is just the CZZ and the CZ bar Z bar. So this is one reason why people chose these coordinates. Now, the reason why I brought that up is because now if you ask yourself what is the symmetry that preserves asymptotic flatness, right? Then the answer turns out to be a little bit wilder if you haven't heard this before. So what happens was that back in the 1960s, before Bondi, Metzner, Sachs, and van der Burg was studying this, there were expectations that it better goes to the flat space at far away, and weak field limits should reduce to special relativity. So in particular, it means that I should expect the asymptotic symmetries to be a Poincare group, right? But it turns out that the ones that can preserve the asymptotic behavior of the metric I show here is actually the whole infinite dimensional Lie group called the BMS4, the Bondi Metzner Sachs group. I put the number 4 here simply because it turns out that in higher dimensions, their stuff, they are different. So I think as a physicist, we are already familiar with of every nonsense. Okay, so the Lie algebra is actually very similar to Poincare. It's a semi-direct product of the Lorentz group, but instead of just with the 4 translation, you also have an infinitely many super translation vector fields. And this is an asymptotic Killing vectors that we call super translation, and the leading forms takes the following form. But what's important here is that this F is not just constant. Okay, it is in general in the coordinates I showed previously, where you include the z and z bar as the angular part, this F would be a function of z and z bar. So what this means is that this is actually a generalized translation of some sort, and it includes the higher powers. And what this implies, and I cannot possibly go through this in just 1 hour, is that this means that the vacuum is actually degenerate. By vacuum, I mean both classically in terms of Minkowski space as the vacuum of the Einstein equations, and also the quantum field theory that comes with it. So what this means is that if you didn't have BMS, right, you would have concluded that the unique vacuum of the general relativity is basically that one single Minkowski vacuum. But what this does is that there is a hidden f z, two functions of f z comma z bar that parameterizes an infinite family of Minkowski vacuum. They are all diffeomorphic, but they are not physically equivalent. And this is kind of like analogous to spontaneous symmetry breaking in phi-4, where you have like the double head potential, and in the case of the phi-4 in the Goldstone boson case, right, you have the whole one U1 parameterized vacuum of the theory. So I'm skipping a lot here, but what's important here is that the vacuum of the Minkowski vacuum in particular is degenerate. It's not just a single unique one that you can consider just by diffeomorphism. And the technical term that I think this group may or may not like is that they call this large and small gauge transformations. So super translations in particular are what they call the large gauge transformation. These are the gauge transformations that do not reduce to identity transformation as you go to Scri+. In contrast, the small gauge transformations are the ones that we always do in electromagnetism. The one that you put a gradient of a scalar potential. You realize that what happens is that hidden in those assumptions, we have been assuming that the chi should have some behavior at infinity. And that's actually what's happening here, is that small gauge transformation are those that are physically equivalent, and they all need to satisfy certain fall-off conditions at Scri+. And the crucial thing is that if they don't reduce to identity transformation at the Scri+, then they are actually the large gauge transformation. And the large gauge transformation will have physically inequivalent, they will describe physically inequivalent transformations. Now, one way to think about this is that basically, even though manifold-wise, the two spacetimes might be diffeomorphic, but from the covariant phase space level or the radiative phase space level, they are actually two different things. So that's the hard part to digest if someone haven't seen phase space in general relativity before. So yeah. Now, another way to see that this is a generalized translation in an angular dependent manner, or in some transverse direction, is that you can actually think of this super translation as actually a generalized translation in the U direction in terms of spherical harmonics. And you can actually show by direct computation that the L equals 0 is just time translation, and L equals 1 is going to be just the spatial translation in weird coordinates. So in general, the supertranslation is going to be the transformations for arbitrary sums of the spherical harmonic expansion. So far, so good? I think I saw Bruno hanging.
You saw Bruno what?
Like he's frozen, I think.
I don't see him on video though.
Yeah, I think it just disabled his video.
Okay.
I think this is really, it would be nice to see the relationship between, Eriksson?
And now Eriksson fell like this. Yeah, I don't know.
Oh, right, it was a problem with Eriksson. Yeah,
So
sure.
I think that Thales, you probably did something to him. You were talking.
Oh, yes, for sure. Well, it's the recording, right? But yeah, I'd like to hear what Bruno has to say about the relationship between these large gauge transformations and the things that he used in his black hole project.
I can stop the recording until he comes back.
I think, which is like, I would like to see the relationship between these large gauge transformations and the work that Bruno did with his black hole thermodynamic one. But it's not a question for you. It's more of a question maybe to Bruno. I don't know.
Yeah, I think that's a question more for Bruno, because I think Bruno is that part of, if I understand correctly, they are doing something a little bit different but related, because they are doing a 2D CFT on the horizon. So I don't know if that's right, but
so Bruno doesn't seem to be online. So maybe you can tell us, Eriksson, all the things that we didn't get to hear.
okay. So can you remind me where I stopped?
I don't remember.
As in Thales was asking me somewhere.
It was,
it was in that slide, yeah.
This slide
it
was
wasn't that slide.
This slide?
Yeah, this one.
This was
Okay.
the
The end
last
of
one you
this,
talked
yeah.
about. Yeah, you got to basically the end of it, I think.
Okay, so I will just recap the last bit, which is that basically one way to think about this is that this is a generalized translation, because you can see that if you do a spherical harmonic expansion, right, then the L equals to 0 and L equals to 1 are just the usual spacetime translation. Do you get that part?
Yes, you said that. Yeah.
Okay, that's great. Okay, then I'm not talking to myself too much then just now. Okay, so this one is a little bit of a big jump, but the problem is that this thing is a research program that recently started, I think, in more on the East Coast side of the US. That there's this thing called an infrared triangle. So I think some of the members of the group did a reading group with me on this a few years ago, and I essentially gave up a while back. But essentially what happens is this. Okay, this triangle is saying that gravitational memory I showed in the first slide is connected to asymptotic symmetries that I just finished talking about, in the sense that two physically inequivalent vacua can actually be the underlying manifold is actually diffeomorphic, which means that the memory effect is going to be the one telling you that there is this physically inequivalent thing going on. And one thing in this corner that maybe all of you are more familiar with than me is the Weinberg soft photon theorem and the soft graviton theorem. In this case, it's actually soft graviton if we are in the gravity side. It's basically a statement about the S matrix, the poles in the S matrix, which is in the momentum space, right? And what happens is that those poles, very roughly speaking, if you do a Fourier transform, right, then you're going to get the step functions. And those step functions are exactly the DC effect you're going to see in a memory effect. And that's actually how the computation goes. On the other hand, if you remember word identity, which I don't, what happens is that word identity connects symmetries with the scattering S matrix. I think it's a contraction of the M mu with some null vector equals to 0. And those things, so the word identity is going to connect whatever super translation stuff or the Lorentz group stuff that happens to the soft photon theorem. So whatever the theorem says here is basically a statement that there is something about the asymptotic symmetries that you have to take care about. And this is a little bit unusual because for the most part, before 2014, most people are doing QED basically ignoring this, even though the asymptotic symmetry as a concept itself is already like 50 years old by now. And that's, if you want, you can take a look at this book called IR Structure of Gravity. It's actually a very nice book. So that is kind of like a jump, but I hope to have actually given you some kind of like an interesting starter if you haven't heard about this concept before. But let us go back to a more down-to-earth topic, which is shockwaves. So the question comes from the fact that supertranslation is a generalized translation, but it looks like a very complicated object, right? So how do you even in principle do this, like let alone in practice, right? One way is to actually use gravitational shockwaves. So in the context of soft hairs on black holes, right, Myers, Perry, and Strominger have used this to basically argue that black hole information has to at least take care of these soft hair contributions before you claim that you have won the black hole information paradox, because it's proven, or at least it has been argued, that soft hair is not sufficient to solve the black hole information paradox, but it looks like it is necessary. And also, second is that there has been recent studies on flat background by Comperellon, Riegler, and also Kolekar, Jorma, Luko, and Maggi on flat space background gravitation, like gravitational shockwave without the black holes. And I will explain to you what I mean. So what I mean is that you consider the simplest nonlinear solution that describes a shockwave, which was due to Dre and Tuft, and this generalized a very famous shockwave solution by Eichelberg and Saxel. So the metric goes like this. The metric, okay, let me bring the mouse. The metric looks like this, and you realize that the main thing that's different is this delta localized shock contribution with a transverse coordinate dependent function. And this metric, you can show that it solves the full nonlinear Einstein field equation with this stress energy tensor, and with this rho here is a function. So the Einstein field equation reduces to a two-dimensional Laplacian on rho, and the energy condition basically requires that this thing has to be positive. And the reason why the shock wave is going to work out is because you can actually realize that this metric is actually obtained simply by doing a planar supertranslation. By planar supertranslation, I mean I'm doing the supertranslation like this, and planar is because instead of theta and phi, this is in terms of x and y, because I'm propagating the shock wave in the z direction. So once you write it in this manner, you realize that the metric is nothing. The shockwave metric is nothing but a flat space metric, but with a heavy side times a diffeomorphism acting on the metric. So from the perspective of the space-time diffeomorphism, right? The Minkowski space-time, the flat part after the shock and in the causal future and the causal past of the shock, right? They're actually diffeomorphic, because this is just a Lie derivative of a diffeomorphism. But of course, since supertranslation is not the symmetry of flat space, then of course it makes sense that this metric G mu nu is not flat. Okay, it has a curvature somewhere. And the beauty of this is that this shock wave is solvable exactly for the massless conformally coupled case. So you can do the usual prescription, and then basically the way to do this is that just solve a flat space scalar field until you hit the shock wave at u equals to u0, where it is localized shock wave, and then do the supertranslation there on the modes by doing like exponentiation of the Lie derivative of that thing, and then just evolve it to asymptotic future, and you get a full solution, and then you can just write the Klein-Gordon the usual way. And this would define the in modes of the quantum field, because you start off from asymptotic pass, go to the shock, super translate, and then go to the future. If you do it the other way around, that means you start from an out state, from asymptotic future, and then evolve backward, you'll get an out state.
This description of the calculation was very nice. I really enjoyed it. Thanks, Eriksson.
Thank you very much. And the best part of this is that it comes out, remember the step function of the memory effect? It literally just appears here. Okay? And if you kill off that part, it's just a flat space Whiteman function written in null coordinates. So I'm not sure how many of you are familiar with doing quantum field theory in null coordinates, but essentially this k minus k plus v here are going to be the null coordinate kind of, it's a null, is a null coordinate version of the mode decomposition, and this is usually commonly identified by this pesky factor that you don't encounter often, which is the transverse squared divided by k minus. Okay, and what interests us recently was that these modes have been mainly used the usual 1984 ways, Birrell and Davis kind, which is to analyze the Bogoliubov coefficients. And the Whiteman function was only considered like literally a few months ago, but it's actually incomplete, which is one reason why we are going to do this. But what is common to all of them is that they claim that vacuum states of the field simply do not remember the shockwave. So in particular, if you want to see the effect of these things, right, the quantum field somehow has to be in the excited states at least. For example, in a Folkwave vacuum. And so we embark on the question of what about detectors, right? Because I mean, I was part of the detector side by now, and Finn was part of Rob's group, so we kind of asked ourselves what will happen. In fact, I gave this archive review to Rob's group about 3 years ago, and it stayed in Finn's head for like 3 years. But anyway, so the Whiteman function, if you have the global modes, right, you can of course solve the Whiteman function. It's just going to be the integral of this u times the complex conjugate, but you cannot solve this.
I don't understand the claim though that so the Whiteman function, the vacuum Whiteman function is different if the modes are different. What does it mean that it doesn't remember the shockwave?
Yes, and the reason is because these guys, they computed the Whiteman function and claimed that they verified Bogoliubov one, but actually, trivially, it is somewhat trivial, but their Whiteman function, they are only computing on each side of the shock.
I don't know. Okay.
So that means their Whiteman functions,
so
right?
If I have the delta Whiteman, if I compute the difference between the two Whiteman functions, let's say flat spacetime and with a shockwave,
yes.
What do I get? Do I get something that has support only on the shockwave or not? Or are there
yeah, the crucial point is that your Whiteman depends on two spacetime points, right?
Yeah.
If you take the 2 points to be on the same side of the shock, right, then you won't see anything, right?
Mm-hmm.
But that's what exactly the paper number 3 was doing.
Okay, gotcha. That's what they mean by it, remember. Like after has passed, it looks exactly the same.
Yes. So they are computing 2 points on both sides, 2 points on the same side of the shock, and they claim that regardless of whether the shock was there, the Whiteman function just don't see it. But we claim that this is basically kind of trivially neglecting the contribution of the theta, right? Because the simplest way to do it is to pick 2 points on either side, right?
Yeah.
Which is what entanglement harvesting would have done.
That's right.
Right, and that's exactly what we are doing. And in fact, there's single detector result that might be of interest to you also. But essentially, the beauty of it is that, for example, if you pick F to be some simple cases like this one, like a quadratic one, this is basically maybe unphysical in the sense that it is a planar uniform density shock. But this is one way people get the solution to the vacuum domain wall. What happens is that this solution will allow you to solve the Whiteman function exactly. And if you just stare at this, right, this Whiteman function just basically looks like the free space one plus a shock-dependent angular piece, because this xi and xi are the transverse dependent piece, because these are transverse these xi and capital Xi are the transverse part, but crucially, there's also an overall multiplication factor by a 1 over square root of the shock-dependent pieces, and this is going to be the important part that we'll see, because this is actually the part that doesn't happen, for example, for linearized gravity. So, but the moral of the story is that, just to reiterate for the third time, that this theta is basically the DC effect from gravitational memory. And that's why the Minkowski spaces on those two sides of the shock, they are not actually the same space-time from a physical phase space language, even though they are diffeomorphic, really. And so, let me reiterate the question of what happened. Okay, so supertranslation charges has been associated to black hole information paradox, and in those cases, they have a trick to use Schwarzschild background and send a linearized shockwave. Of course, the word linearized is important because they don't have an exact solution, but it's an argument. And there's a large program that's trying to understand holography from this perspective, holography in asymptotically flat spacetimes, because technically you go into one codimension one hypersurface on Scribe Plus. Now, the big question is, do Bach's shockwaves leave imprints on quantum fields? And I will reiterate, the point was that the previous calculations show that the answer is no if you are only restricting yourselves to vacuum states, but if you go to higher excited states, then you do. But actually, in hindsight, it's kind of obvious why it has to be. But the problem we had was that even if we believe they were right, then this comes as a surprise, because in the end, gravitational shock waves is just another gravitational waves, right? It's a very different kind of gravitational waves, but in the end, it is a radiating spacetime. It carries something to Scri plus. So if the linearized gravity already can affect vacuum entanglement, then we don't see why this thing has to be true, right? And of course, Eduardo already see by inspection that, of course, that has to happen, right? In our case, it's on hindsight because we try to brute force compute the Whiteman function, and after the expression comes out, then we realize that has to be the answer. And this is also kind of reminiscent of anti-Unruh effect, right? Because in anti-Unruh effect, what you notice, apart from all the beauty of the effect, is that this is an effect that is kind of like something you only see when you have detectors. Like, it's not something just calculating, just proving that the state is KMS. It's going to show you that there's an anti-Unruh effect there, right? So what has happened here is that this will be another example where the Bogoliubov coefficients are actually going to be blind to something else, even though you're using localized observers. And in the next few slides, it's going to be something you are very familiar with. I'm going to go through very quickly, but if not, please stop me. Okay, so what we are going to do is to consider simply the entanglement harvesting protocol right from the beginning. So I already assume that I have two detectors. The reason is because if I just want a single detector result, I will just ignore the second one. And then the total Hamiltonian will be just a sum of the local Hamiltonian where A interacts with the field, B interacts with the field locally, but they don't crosstalk to each other by some entangling process. And you take the initial state to be the standard one, which is the ground state for both detectors and the vacuum state. And now here, this is the thing, right? Because this vacuum state, since it is highly degenerate, right? What happens is that in principle, one could have considered a physically inequivalent vacuum, but let's ignore that for now, because in our case, this vacuum is defined by the shockwave geometry in modes that were already computed. And the standard calculation apply. You can compute the entanglement between the bipartite state after evolution. And one way to use this is to use concurrence. Some people prefer to use negativity. That's fine. But I think for now, let's use concurrence because it cleanly separates the non-local part M, which depends on both detectors' position, versus the local noise part, which depends on just the excitation probability of each one. Now, the good news was that the Whiteman function, we could find a closed form expression. But the bad news was that this one, when the density matrix elements itself, you cannot really find the exact expression. So I have to resort to basically numerical contour integration. I couldn't find any other way to do this. And this also means that certain extreme parameters that some of the people in the entanglement harvesting projects might be interested in will not be accessible using this one, but we can do something nonetheless. And one important thing that might merit some care is that you will ask, with shockwaves, how do you describe the trajectories of the detector, right? Now, if you localize the detector switching so that it doesn't touch the shock, then there is no problem, right? But the problem is that you have to at least make sure that if you want to choose inertial trajectory to be as close as the flat space one, to make a comparison with the flat space results, right? Then you have to solve the geodesic equation. And it turns out that at least for the zero transverse direction and for the choice of the shockwave profile we chose, it turns out that the geodesic equation is going to spit out the Minkowski trajectories. So in general, this is not true. For example, if you consider Eichelberg-Saxel shockwaves, right, with this shockwave pulse here at the origin, then what happens is that for time-like trajectories at fixed r, once they hit the shock, they are going to get refracted. So they are going to gain, in particular, some fixed velocity. And if you consider a more like wider pulse or something, right, then this velocity might even be time dependent. But in our case, it actually works out because we chose a toy model to work with, and that toy model happens to be kind enough to us. And there's some interesting things going on here, because I think some of you are also familiar with the fact that you cannot multiply distributions, right? But it turns out that multiplying distributions is exactly what you need to solve for geodesics in this kind of spacetimes. And what has happened is that in 1991, Kunzinger and a bunch of other collaborators like Balasin and Ferreira in separate papers, they have shown that if you adopt this thing called the Colombel algebra, I don't know if I pronounce the French name correctly. Essentially, this is an algebra on distributions that allows you to multiply distributions. Now, of course, you know that the theory of distributions already tell you cannot in general do this, right? So you must have given up something. And the answer is yes, you must have given up something, in the sense that the products of distributions has to be considered case by case. So for example, in this particular shock geometry, right, it turns out that the rigorous way of doing this is actually the same as the cheap treatment of distribution. For example, in calculus, if you just look at a graph, someone who are in first year undergrad might have thought that if I multiply two step function, I should get the same step functions, right? And it turns out that if you do this for this particular case, it's going to come out right. But in some crazy cases, actually, you have to account for the fact that the discontinuity in the step function might be ambiguous, right? Some people define the origin of the Heaviside to be 0, 1, or sometimes half. So in some cases, you have to actually take half. But sometimes you can choose whatever you want. But in this case, this thing works out. So that's kind of one way you pay the price for being able to multiply distributions, is that it is not going to be general. The rule is going to not to be general enough for everything. So the setup we are going to consider, at least for the two detectors case, is going to be something like this. Okay, so we put two detectors on either side of the shock, and they are going to be localized with some Gaussian strong support for the switching of this kind. And we might be considering, for example, moving one detector while fixing the other one, and sometimes one detector's Gaussian profile is going to cross the shock. Okay, and later we'll also see that if we consider just one detector case, then let's just forget about the second one. But this setup should be familiar to everyone, except that there is this dotted diagonal line which describes the shockwave at the origin at u equals to 0. And the results are preliminary. We are still finalizing it, but I think this part is fine. Is that, first of all, this plot shows how the concurrence and the m term, the absolute of m, and the square root of PAPB, which comes into the definition of concurrence, vary as you change the position of Alice's detector and move it towards Bob's. So Bob is currently at ZA equals to 7, while Alice, you start from -7 in units of t, and then you slowly move them. And what's interesting here is that if you look at the green one, right, the green one is a single detector excitation. So the moment you start climbing up and form a peak, that's where you know that the Gaussian has touched the shock, right? But what's interesting here is that means, right, the non-local correlations actually climb up slightly earlier than that. So this is actually kind of funny, because it tells you that indeed two detectors do get extra information from the non-local correlations than just a localized one. Because the localized one, you have to be somewhere here before you actually start seeing something, because that's where you actually cross the shock. And the other second dotted here, this is the line where I declare that the two detectors can now communicate, because the Gaussian support is finite, right? Which means the light cones might be talking to each other. So if the detector is already here, then this increase in concurrence is actually just because they are mainly coming from the communication component. So this part is actually the interesting bit, and this one depends on the stress energy tensor of the shock. Now, so this one is actually enough to argue that there is something really interesting going on for two detectors. But let's step back. How about a single detector, right? Because maybe a single detector already has a lot of story to tell. So for example, if you look at Alex Smith, Qu Xu, and Ahmed, right? they show that a single detector does not sense gravitational wave in the linearized gravity sense. So they use this metric in the BJR coordinates, and they show that the first order correction of the flat space Whiteman function vanishes. In particular, this first order correction in where A is a gravitational wave amplitude, they show that a single detector don't see this term at all. Now, can we see what happens?
They did it for point like only, right?
Yes, we also do point like because we want to avoid unnecessarily crossing the shock. We could, but another reason for us we also consider point like is because practically speaking, I already had to do numerical integration just for point like detectors, so it would be very horrible if I did.
There's an argument to be made that spherically symmetric detectors may not see them, but any non-spherical distribution might.
Exactly.
That's right. So in principle, there are a lot of things to argue about it. I mean, you can also use electromagnetic field, and maybe the dipole can see something, right? But essentially, let us just look at this first. The claim that they say that for a single detector they don't see anything. Now, another thing also, you must have noticed that the delta x squared minus delta y squared, this is basically another way to see that if you are not spherically symmetric, you might see something, right? So, but what if we do a weak Shockwave regime? That means we consider the stress energy tensor is weak with respect to some scale, and then we do a series expansion of the Whiteman function in terms of the energy density of the shock. What you will get is that you will get a correction to the Whiteman function in flat space with actually a linear term containing here, and then a quadratic term in here, and then the higher order terms. Now, for them, the linear term, they claim that the linear term doesn't contribute to transition probability, and therefore we don't see anything. Now, in shockwave geometry, this generally contributes, but now linearized gravity solutions that they use is a linearized vacuum solution to the Einstein field equations, right? It's a gravitational wave propagating in vacuum. So that means if we were to mimic what they do, we should be setting the trace of A to be 0. The reason is because the only non-zero component of the stress energy tensor is actually proportional to the trace of the shockwave profile matrix A. And if you set this to be 0, even in the shockwave geometry, you do get the fact that actually the first leading order correction is actually the second order. So to leading order, we cannot see a single modification to the single detector one. However, there is a catch. In our case, because this is a non-linear solution to Einstein field equations, this second order contribution never vanishes, right? Because this A squared, trace of A squared never vanishes unless A equals to 0. And same for this. While this one, you can at least set it to 0 by choosing the diagonals correctly. But in their case, they cannot actually check that this second order one matters, because if they go to second order in amplitude, they are going to break the regime where linearized gravity is valid, because it doesn't solve the Einstein field equations, the vacuum Einstein field equations in the to second order. So one way to see this is that if you consider the traceless one, right, the so-called the vacuum nonlinear solution to the shockwave, the sourceless shockwave geometry, right? What happens is that the shockwave geometry is gonna be basically just adding noise to your transition probability, which may be reassuring, because if I guess in general, you expect that stuff that passes through you is gonna be just increased excitations. But actually, this expectation is not quite general, because if you consider the trace to be non-zero, right, you will realize that actually so long as your stress energy is small enough in amplitude, then actually the noise decreases first before it generically climbs up. So one way to see this is that actually the culprit is this minus sign here. So it actually gonna try to reduce something first before the integral starts to do something funny. So this is another peculiar thing, because that means in this regime, right, you might be able to just gain this might be one reason why the entanglement gain by the detectors might increase, just because there is this reduce in noise. But of course, you have to compare this with the modification to M. Okay, and that's the end. So I put the code up there because I learned this recently, is that audience are likely to only remember 3 things from your presentation. So I divided the presentation into 3 pieces. But basically, hopefully, I've covered a little bit about gravitational memory and asymptotic symmetries, shockwave geometry, and how it connects to planar supertranslation, and how Bruno with detector would be seeing them. So this quantum imprint thing is basically a very recent kind of like a David Kubisnak kind of stuff. And the end. I don't know if you have any questions, but I hope it's not too boring.
No, I think that was good, by the way. I think that there's not. Why do you call it a quantum imprint? Why quantum?
Oh wait, it's just a David's term, because the imprint is on the vacuum state of the scalar field.
Yeah, but it could be in the sense that it could be classical correlations as well. I mean, as in like it's not.
Yeah. So the word quantum here, we just mean the quantum one. We don't mean that the imprints are only quantum correlations.
Right. Okay.
Yeah. How long was that?
I don't remember when you started, to be honest, because the conference shift everything, and I don't know when we finished. But
okay. Anyway,
probably around an hour, I would say.
No, I think we start at 1. So I think that's fine.
We started at, it wasn't 1 yet when we started.
Okay. Anyway, I think yeah. So this is a little bit of a rush, but I hope this gives you something funny, because to me the main message of this is that technically EQFT in curved spacetime should be now thought of in terms of the BMS group rather than our Poincare. But anyway.
All right, cool. Questions, people? Yeah, and any Eriksson, we can. In my opinion, we can post this talk. There's nothing to be. I don't know. I mean, up to you. But it feels to me that I can post it, no problem.
Okay, so if you think you're happy with it, then that's fine. Because originally I thought this is gonna be a terrible talk, but
oh no, it wasn't.
It turns out okay, I think. Yeah.
All right, cool.
Okay,
nice. Thank you, Eriksson. Let's thank Eriksson. People are not that person. Let me start the recording.